Thank you very much. Good afternoon, everybody, and Happy New Year. What happened to my picture? Can I have the overhead, please? Thank you very much. Good afternoon, everybody, and welcome to EE 544, which is called RF Systems and Hardware. Let's go over some course administration issues before we start with the topic at hand. My name is Professor Zahid, Z-A-H-I-D. My office is PHE 418. PHE stands for the Powell Hall of Engineering. Powell Hall of Engineering 418. This is my phone number. The lecture hours, of course, is Tuesday and Thursdays, 3:30 to 4:50. This is our class, All in Hall of Engineering 132. The discussion hours is on a Friday, 1 to 1:50 p.m. All in Hall of Engineering 122. 122 is the studio just outside. And your first discussion session will be this Friday. So, I mean, you know, the school has started already. So, we have a discussion session. We'll talk about discussion session in just a second. My name, again, is Professor Zahid, Office 418. Office hours, 9 to 10:30, 12:30 to 1:30 p.m., 5 to 5:30 p.m., 7:30 to 8 p.m. I can also stay after 8 p.m. if you need me, provided that you walk with me to the parking lot at the end. Because it will be dark, I need a bodyguard with me. You will be my bodyguard. So, just keep that in mind. I will also schedule the extra office hours before the midterm and before the final on Fridays and on Saturdays. Clear, before the midterms and the final exam. This is the email, azahid@usc.edu, and the website. Everybody have access to the website? Everybody? Okay, good. The prerequisite of the course, actually, it's endless prerequisite. And you will see why when we get to the material. This is one of the hardest class available in the department. And you will see why in just a second. RF is not an easy topic. It's not an easy topic. And you will see why in just a second. But look at the prerequisite, 348, which is electronic circuits. Most important to me is the CMOS. Clear, the MOSFET, operation of the MOSFET. I assume everybody has taken electronic classes? Everybody? Okay, fine. EE 301, which is linear systems and signals. Review of linear systems and signals. What we need from here is, for example, the Fourier Transform. We need the Fourier series, or not Laplace Transform. We don't care about the Laplace Transform. Fourier series, Fourier Transform, all of these signal analysis, systems, convolution, and so on and so forth. And this, by the way, will be the topic of your first discussion session. The TA will give you an overview in case you forgot it. They will review it. He will review it for you. Probability theory for engineers. This is the oldest type, the old class. But we really don't need a probability for that. What we need from this course is that you get a feeling about the noise, because we are going to study heavily the effect of noise, how we design our circuits based on the noise, and you need to always remember that the noise is a random signal. Clear? So we cannot talk about noise as if it is a deterministic signal. We need to talk about what? The mean square, the averages, and so on and so forth. All of these things. So, I mean, don't get scared of this. You tell me I did not take any course in the probability. We don't need a probability in this class. Clear? I just wrote it just in case of the noise. That's why I wrote the noise here. Okay. EE 467, 475, 467 is called communication system, 465, sorry, 475 is wireless communications. Forgot what this is, 484 something communications. In other words, some background in what? In communications. Clear? And again, we will discuss this as we move along. In this course, we will learn some CAD tools, including MATLAB, SPICE, Cadence, Spectra RF, Agilent ADS, and so on and so forth. The TA will guide you to the tool that you will be using for your simulation project. You will have two projects. MATLAB, nobody will teach you MATLAB. You should know by MATLAB by now if you are RF engineers or communications engineer. Clear? Most important to all of these, more important to all of these five is the sixth bullet, which is the passion and the dedication to the course. You follow me or not? RF is a fascinating topic. It's a fascinating topic. I cannot emphasize it enough. However, it's a very difficult one. You will see why. Again, when I show you a chart, a simple chart. One second. When I show you a simple chart, which I have no idea what it is, let me see if I can find it quickly. I will show it to you shortly. I have no idea what it is. I will show it to you shortly. You will see that to deal with RF, you need to have what? Knowledge or background on many other fields in addition to the RF. RF is not a standalone topic that you only need to study RF to be good at it. You need several other stuff with it. I will show you that in just a second. A textbook, we do have two textbooks. Both of them are required textbooks. Microwave and RF Design, second edition by M. Steer. And RF Microelectronics, again, the second edition by Professor Razavi. Professor Razavi is at UCLA. Professor Steer is in North Carolina State University. Both books are very good books. One of them is heavily oriented toward the system aspect. The other one is heavily oriented toward the circuit aspects. The course, if you look at the title one more time, the title is what? RF systems and what? Hardware, which means that we are going to be covering both the systems aspects and what? The circuits aspects, the hardware aspects, as I will show you in just a second. Clear? Okay. Now, probably both of these books are on the web if you can find them for free, the PDF or something. You know, it depends on your ingenuity. You know, you guys have some certain magic to find all of these things, but you need the textbooks. Now, our teaching assistant is Mr. Aaron Fries. The teaching assistant is not an RF guy. So most of the time he will be helping you with the circuits. You follow me with the simulation. Questions on the RF topic in general or pertaining to the course, you need to depend on me. He is not an RF guy. There are no RF guy. In other words, the department does not have TAs to assign for me. So his specialty is in quantum communications, but he is well familiar with the what? With the tools, with the Cadence tools and with the Agilent ADS and so on and so forth, Spectra RF and so on. The email, I don't know why this one is not showing it here. Can you see it in your charts? Okay, I need to make it darker here. Okay, the email is written here. Office and office hours, he will be posting it shortly on the web. So I have no idea what they are, but their office hours do not overlap with mine. Because if they overlap with mine, nobody will come and see me. And I will be lonely in my office. I don't want to be too lonely in my office. You need to come. The course is not an easy course. It is a very hard class. So I expect you to visit me often to the office. Don't get scared. This mustache is fake. I can remove it if you want. So you need to be what? Via email, via office. You need to continuously drop by my office, ask questions and stuff like that. Clear? His responsibility is maintaining the course website, conducting a weekly discussion session, mainly on what? CAD tools, mainly on the tools. He will also review some material from the electronics, especially the what? Amplifier, the MOS amplifier, and so on and so forth. Conducting office hours, assisting students with their homeworks and simulations, designing and grading the course project, one of the project, not the MATLAB project, but the circuits project. He will design the project, and he will guide you, and he will also grade it. We'll talk about the homework in just a second. All emails, when you do have any email on the homework, you need to address the email to him and CC it to me. The reason that you want to CC it to me is two things. First of all, I need to make sure that he responds to you in a timely fashion, but more important, I will ask him to include me in his response, so I need to make sure that he gave you the right what? That he gave you the right answer, and if I want to add, maybe his answer was not very clear, I need to what? I need to make it clear. I need to make it clear. I need to what? Add my, let's put it this way. I need to add my 2 cents to the response. Clear? Okay. You will see, by the way, throughout the semester, you will see that eventually you might always depend on me to answer your question, which is fine. I will not what? I will not complain about that. And the reason for that is because, again, as I told you, he is not an RF guy. I'm hoping, by the way, that some of you will be really good at this material, that you will help me the next time the course will be open. In other words, the next time you will be what? You will be helping me, because you will be what? You will be really good at this material. Clear? Clear? Okay. Now, the course workload, this is very important for you to understand. The midterm is on a Friday. It's not on Tuesday or Thursday. It's on a Friday, March 7th. It is from 4 to 6 p.m. or 6 to 8 p.m. I will have 2 sessions. So if you feel more comfortable at the 4 to 6, come at 4 to 6. If you feel more comfortable at 6 to 8, come at 6 to 8. However, only keep in mind that if you take the exam between 4 to 6 and you decide to leave after 1 hour, let's assume you finish the exam after 1 hour, which is very doubtful, by the way, which is very doubtful that you will finish it in 1 hour. You cannot leave. You have to stay there until what? Until the time is over before you leave. Of course, the second session, no. You finish after 1 hour, good luck. Did you understand what I just said? Okay, good. March 7th. The final exam is Tuesday, May 13th. Tuesday, set by the school. May 13th, between 2 to what? 2 to 4 p.m. Clear? Clear? Okay. There are no makeup exams. So if you are, for example, if you are traveling, if you are sick, if you are dying, you don't need EE 544. Go ahead and die and get it over with. If you are getting married, if you have an interview, I don't care. Drop the class right away. I do not give makeup exams. Clear? Okay, good. Now, so there's absolutely no makeup exams, no matter what your reasons are. Roughly 5 to 6 homeworks. Now, I have already found a grader. However, I need approval from the department because this course belongs to the electrophysics rather than belongs to the systems group. Did you understand what I just said or not? The electrophysics are very stingy with their what? With their grader assignments. If they approve the grader, then the homework will be graded. But if they do not approve the grader, or they tell me we don't pay you for the grader, or we don't pay the grader, then the homework will not be what? Will not be graded. Do you understand that or not? Will not be graded. I don't have time to grade homeworks. Clear? And neither the TA, because the TA is also another TA of another class. Did you answer what I just said? So this is wait and see. Now, doing a homework, whether it is graded or not, is most important. You follow me or not? Because that is your opportunity to learn and to apply the material. So don't make it like what? Just because it's not worth any points, I will not do the homework. Clear? Now, after I assign the homework, when it is due date, we will what? I will be posting the solutions. But believe me when I tell you, if you wait to read the solutions without trying the problems yourself, you are doomed. You are doomed. Do you understand what doomed means? Doomed means what? You are done. Clear? Clear? Okay, good. Graded midterms will be returned. I will return the midterm, the graded midterm. That tells you, by the way, who grades the midterm and the final. I grade the midterm and the final. The TA will not even see the midterm and the final. This is my responsibility. I will return the midterm and the solutions will be also posted, but the finals will not be what? The finals will not be returned, and neither are what? The solutions will be posted. But you are most welcome to drop by my office after the semester is over, to look at your paper, to look at the solutions, to ask questions. You are most welcome to do that. but I will not return it. I need to keep a souvenir of our time together. Clear? So romantic. I will keep what? I will keep only graded finals. Did you answer what I just said? Okay, good. There is absolutely no curve in this course. If you are looking for a curve, you are in the wrong class. I don't go by a curve. So the midterm is 40, final is 40, the project is 20%. This one might be added up a little bit if the department approves of the homework of the grader. So it might go to what, 30%, and we reduce this one to 35, something like that. Throughout the semester, I will also assign a couple of extra credit. Most of them involves the use of Excel. So think about them as what? As mini projects, but they are related to what? To the RF link design, for example, or spectrum allocation, generation of the intermodulation components, and so on and so forth. All of these things. Most of them would require you to use Excel. I'm assuming that you know how to use Excel. Okay, if you don't, there is some problem in there. The extra credit will be added to your midterm score. And if your midterm score plus the extra credit goes over the 100, so be it. My heart will become like this. I would say my students is working hard, both in the midterms and the extra credit, and they deserve everything that comes their way. So for example, just for sake of argument, to make the math simple, if the midterm is worth 50% and you get a total of 110 out of 100, that translates to what? 55 out of what? Out of 50. Did you get my point or not? So I will give you 55 out of 50 so that you can come to the final exam a little bit more relaxed. This is the grading scales, 80 to 100, A minus to A plus. I don't think there's A plus, but anyway. 65, 79, B minus to B plus, whatever. Clear? Clear? Oh, again, I'm going to repeat this one again. I hate to do that, but it's reality. RF is a very hard class. Do you follow me or not? It's a field that companies fight for it to find a good RF person. Are you following me or not? It's not easy. Clear? And you will see it. You will see it right away. That's not an easy class. And that is when I want you to what? To work harder and to depend a little bit on me to what? To clarify the material for you. Email me. Do not hesitate to email me. By the way, you will be surprised of how quick I return email. You will say, what? This guy does not have anything better to do than to sit answering email? The answer to that is what? Yes, he does not have anything better to do than answering emails. So do not hesitate. The objectives, of course, is to what? Is to learn the basic principles of what? RF wireless. Our course is basically on the design of the wireless transceivers. Transceivers is an abbreviation of a transmitter and what? Receiver. Clear? So it's a design class. Design and analysis of the RF front end. I'll explain to you what a front end means, and the digital baseband back end. The digital baseband back end is a topic of another class, but I will give you just an overview. Our interest will be only on the what? On the front end. Clear? I will show you the difference between them. But if you are interested in the baseband back end, this is where the ADC, anybody? Analog to digital converter, and the DAC, which is the digital to analog converter, takes place. This is EE 536B. I'm not sure why it was canceled this semester. I am a little bit not happy about it, but it was canceled this semester for some reason. Anybody wanted to take this one? It was canceled for some reason or another. I have no. No? No, I don't want you to tell me why, because what do I care? I thought you said no, it was not canceled. I don't want you to tell me why. But I will give you an overview so that you get a big total picture of what? Of our transmitter and receiver. Clear? But we cannot go into the details of the DAC and the ADC analysis. Clear? Or design. Now, we will also learn design methods or techniques for the RF circuit design, and mostly in the what? In the CMOS technology. CMOS stands for what? Complementary metal oxide semiconductor. Clear? And again, as I told you, I'm assuming that you do have background in the basic operation of what? The CMOS, especially the mode of operation. When we say that the CMOS is in the what? In the cutoff mode, in the what? In the triode mode, or in the saturation mode. Are these ringing a bell or no bell? If it is no bell, it means what? You need to clean the bell very quickly. And this weekend, you need to clean it very quickly. Okay. Evaluate the performance and limitations of various RF transceiver architectures. By performance, we talk about what? We talk about the trace between, for example, power, between the noise, all of these issues between the nonlinearity. This course is heavily practical. This course is not your conventional theoretical courses that you have taken in communications, including 564, 567, even 535, which is a mobile communications class. All of these classes are what? Theoretical classes. This one is heavily what? Practical. You will hear some words that you haven't heard in what? In the other classes. You say, what are the, how come I did not hear it in the other classes? You did not hear it because those other classes are heavily what? Theoretical. This one is heavily what? Practical. These words that we will be using are only the words that you will be using when you work with leading companies, the Qualcomms, the Broadcoms, the Intels, the Microsofts, the Apple, and so on and so forth. All of these companies that you hopefully that you will have a chance to work with. Clear? Okay, so we need to understand it very carefully. We will get also a general exposure to all types of standards, 2G, 3G, 4G, the Bluetooth, the 802.11, the Wi-Fi, the WiMAX, the RFID. RFID, anybody? It's radio frequency, identification systems, and the GPS, anybody? The global positioning systems, and so on. So you can tell, by the way, from all of these standards that we are dealing with a field that is what? Wide open. Too many standards to learn, and so on and so forth. Clear? Okay. I will be posting, by the way, along the way, tutorials. We cannot cover every one of these standards. So just in case you want to learn more about certain standards, I will be posting tutorials. By tutorial, I mean what? Easy to read without getting deep into what? Analytical analysis or mathematics and so on and so forth. It's just for you to get a big picture, just to help you in the interviews when you go and interview with companies and stuff like that. They are not going to ask you to what? To sit down and do the what? The Fourier Transform or the simulation or something. They are going to ask you what? General ideas to see if you are ready for that or not. By the way, once we get also deeper a little bit into the subject, I will be posting series of questions that companies do ask when they interview people. Clear? The reason I know that because some other students who went through these interviews gave it to me, and I will relay it to you so that you're prepared when the time comes. Now, let's understand before we get to the details what EE544 is not and is. EE544 is not a course on wireless networks. So if you are interested in wireless networks, by networking, what do I mean? I mean are you familiar with networking? The layered architecture. When we deal with wireless networks, we are dealing with layers 2, 3, and above. This one here is basically a what? A physical layer device. Are you following me or not? Sorry, a physical layer course. Clear? We don't deal with what? Routing. We don't deal with what? We don't deal with issues regarding what? Regarding security issues and so on and so forth. This is not a course. The course, if you are interested in wireless network, the course is $597. This course is offered, I think it's offered every semester. I don't know what happened this semester. And also $579. $579 is basically a what? A software-oriented class. Only software. Developing what? Developing models. Developing applications for mobile devices. This course is not. This course is not a course on microwave theory or antenna. I'm going to survey some antennas types for you, but it's not a course on microwave theory or what? Or antenna. These are separate classes. You can take 571 A and B, 573 A and B, and so on and so on. This course is not a course on chip design, which means what? Our design will be basically a what? A circuit level rather than a what? A chip level, which means what? We are not going to integrate all of these circuits into what? Into one chip. This is not this course. We don't have the time to cover what? Both the systems and the what? And the chips here. This is a circuit level course. More in chip design, you might be taking 536A and B. Anybody taking 536A? Was there a chip design? By the way, I don't think even in those courses there are what? Chip design. There's also discrete designs, right? So I'm not sure which class will teach you what? Chip design and stuff. But what I'm trying to tell you is that this is not it. What is it then? This is a course on the design of what? Transceivers, transmitters, and what? Receivers. on a what? Discrete basis, circuits. In other words, we will take, for example, the power amplifier. We will take the what? A synthesizer, an oscillator. We will take a what? A mixer, different types of mixers, active mixers, passive mixers. We will design them discretely. Do you understand what discretely means? Without what? Integrating the whole thing on a chip. That we don't have time for all of this. There might be some other classes you might want to consider those. So it's a course on the design system and circuit levels and the performance analysis of RF wireless transceivers. The first half of the semester will be basically what? Systems oriented. Whereas the second half of the semester will be what? Will be circuits oriented. I cannot begin with the circuits right away if your background is what? Is mushy as far as the systems, as far as the performance is concerned, and so on and so forth. So for example, if we say design some kind of a what? Some kind of a low noise amplifier with an IIP3 of some, let's say -5 dBm. You will tell me, what is IIP3? You understand what I just said? Anybody knows what IIP3 means? Yes, sir. The third order intercept point. Close enough, very good. But do you see my point? My point is that I cannot start talking about what? Design specifications without explaining to you the parameters involved. Are you following me on that? So keep that in mind. The first half of the semester will be heavily oriented toward what? Toward the systems. The second half will be heavily oriented toward the circuits. Clear? EE 544, again, is designed for those hardware-oriented students who badly lack rigorous mathematical background in the analysis of RF systems. How many of you are here circuits guy? None of you? All of you are systems-oriented? Circuits. Okay. Suddenly, I see too many hands. Were you shy? Okay. Circuits people, they hate what? To get into analysis. They are what? Circuits. They understand more circuits rather than communication. Again, by the same token, EE 544 is designed for those who are in communication systems, but who lack badly aspects of what? Design of RF systems. In other words, if you ask them, what is a synthesizer? They tell you, what is it? I have no idea what synthesizer is. Because in the other courses, in 564 or 567, all what you see is a what? Is a block diagram. They tell you that this is a local oscillator. What does that mean? A local oscillator. What does that mean? We need to understand how it works, how we design it, what are the performance parameters associated with it, what are the trade-off parameters that we need to take, what are the important things related to all of these subjects, and so on and so forth. And then when we deal with the circuits, the communication systems people tell you what? What is, I have no idea what you are sketching. What is the circuit? What does it do? So it's a combination, this course. Why it is so difficult? Because it covers both aspects, the systems aspects and the hardware aspects, as you will see in just a second. They are those designed, EE 544 is designed for those with passion for the wireless, RF wireless systems, and who inspire to have a career in this highly in-demand field. Salaries, by the way, for RF engineers, good RF engineers, eclipse those for what? Regular communication systems engineer or systems engineer. Because they know that this is what? Not an easy task. So if they find somebody who has really good background, who understands the concept clearly, they go out of their way to what? To hire them. These are the textbooks. The first two are the textbooks that we are using. This is, by the way, an excellent book on the design of CMOS RFIC. This is a circuit-oriented class by Professor Lee. Professor Lee is in Stanford University, and Professor Steele, I told you, North Carolina State. Razavi is UCLA. These are all other references. They are all available in the library. If you want to browse through them, you can drop by my office and drop by them. But you need to let me know, because I don't have them all in my office. I do have them at home. So if you want to browse through any one of them, let me know, and I will bring it to my home, from my home to the office. You can browse through them. I'm done. No, not done with the class. Done with the administration. Do you have any questions? We are going to have two projects. One project is systems-oriented, using simulation, using MATLAB, performance of different modulation techniques, different aspects, types of determining, for example, the error performances, and so on and so forth, all of these things. And the other one is circuit-oriented, which is design of a certain part of your receiver or the transmitter, whether it's the LNA. LNA stands for what? The low noise amplifier or the synthesizer or oscillator or mixer and so on and so forth. We will see, or power amplifiers and so on and so forth. Usually these classes, by the way, they never talk about power amplifiers. The regular classes, 4, 5, 64, they never talk about power amplifier. They just put it as a block diagram. In our class, we will go deep into the circuit analysis and system analysis of power amplifier. Clear? Most important part in the transmitter side of the chain. Clear? Yes, sir. Cannot hear you, my dear. Raise your voice.
Are we only focused on the? Do we only focus on the narrowband systems?
No, we will cover. Well, that's a very good question. The question is what? Are we going to be focusing more on the narrowband or on the wideband? The answer is that the focus most time will be on the narrowband systems. However, I will give you a couple of examples on wideband, deciding wideband amplifiers and or wideband what? Excuse me, wideband oscillators or mixers. But the majority of the circuits that we'll be talking about is for the narrowband. Clear? Oh, now no, remove my picture. Ooh, so creepy. Remove the picture, please, operator. Yes, thank you very much. Looks creepy. Okay, I don't want my pictures there. Clear so far? Okay, good. Now, let's look at the overview. What is the key word here? What is the key word? Overview, which means what? Do not ask me about detail right now. The details, we will cover it later on. I want you, first of all, before we get into this, to get an idea about the system that we will be interested in. This is the system that we will be interested in. This is a typical wireless transceiver. Remember, transceiver is said to be what? Transmitter / what? Receiver. This is what is known as a super heterodyne receiver. Super heterodyne. We don't know what that means yet. We'll get to it in just a second. But in this class, we are not only going to be interested with super heterodyne. We are also going to be interested in the homodyne. Homodyne means what? Direct conversion receiver. Getting direct conversion means what? Taking the signal all the way from the RF to the what? To the baseband without stopping or without converting to the what is known as the what? IF. IF stands for what? Intermediate frequency. But this is just to give you an idea of what's going on. Clear? So before I give you the overview, let's look at this to get an idea of where we are headed to. Clear? Or do you want me to go over this first? What do you want? Say that again? Let's look at the block diagram, just to get an idea. But do not stop me with questions. Why? We are going to be discussing this in detail. I want you just to understand the buzzwords right now. The buzzwords in the what? In the way I say. Okay. So what? Can you zoom in, please, a little bit, operator? Thank you very much. Okay. I want you to see this. This is a single chain. This is the transmitter. This is the what? Receiver. This is in the same box. These are not two different boxes. It's the same box. This is a transmitter and this is the receiver. This is the antenna. This is what we are going to be referring to as a what? As a duplexer or diplexer. Sometimes they call diplexer or duplexer. It is basically a filter that will separate the uplink, assuming this is your mobile unit. Assuming this is your mobile unit, communicating with who? With a base station. Are you familiar with this or not? I'm not sure if it is a good idea to begin with this or not. Are you following me or not? Okay, good. So this is to separate the what? The two bands. The transmitting band and what? Receiving band. You don't want the transmitter, this is a mobile unit, you don't want the transmitter signal, to be what? To be leaked into your own what? Your own receiver. Do you follow me on that? So we are going to have what is known as a what? As a duplexer in here. Clear? This is what is referred to as a what? As a band select filter. I want you to understand what is the meaning of a band select. Do not confuse the word band select with a channel select. Channel select, you are only selecting the desired what? The desired channel. A band, in a band, there are multiple what? Multiple channels in there. For example, let's take an example so that I will get back to this or not. I'm not sure if starting with this is a good idea, but you asked for it. Did you ask for it? Okay, so, but let's understand one thing here. Let's take an example. For example, AM radio. Just an example, AM radio. Tell me what is the band? Band is what? is roughly 600 kilohertz to what? 1600 kilohertz. How much is the bandwidth, by the way? The bandwidth is the range of what? The range. The bandwidth is how much? Bandwidth is roughly 1 megahertz. This is the bandwidth of the entire band. This is what? Each AM channel, AM stands for what? Amplitude modulation. Each AM channel occupy, help me, anybody. Your radio, 10 kilohertz. It occupies 10 kilohertz. This is a channel, which means what? This band, if you see this band, this is F. What is F stands for? Frequency. This is the channel. Here, 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 and so on and so forth. Every one of them is what? 10 kilohertz. By the way, what do we call this? Anybody? This is the guard band. Separating what? Separating adjacent channels. Are you following me or not? Is it, by the way, is it a waste of bandwidth? It is a waste of bandwidth, these guard bands. But we have to use them because there will be interference between what? One channel and adjacent channel. We'll talk about interference in just a second. How many total do we have? How many channels do we have? The total bandwidth, forget about guard bands, just to make the math simple. I have 1 megahertz. I have what? 10 kilohertz for a total of how many channels? 100 channels, which means what? There are 100 AM channels, AM broadcast. This is AM broadcast. When I talk in your radio, by the antenna, are all of these received? All of these are received. So when I talk about a band select, you are selecting the entire what? The entire band, which means you are rejecting out-of-band signals. Let's take example of an out-of-band. Let's assume we are dealing with FM radio. Help me. 88.1 megahertz to what? 108 point what? Megahertz. How much is the bandwidth roughly? Is 20 megahertz. Who assigns these? These are what is referred to as what? A licensed band. Licensed by the what? FCC. They license it to the what? To the broadcasters. Are you following or not? But these are free. Free what? The FCC assigns it to those broadcasters for the benefit of the what? For the benefit of the public. Disseminating information to the public. This is unlike your cellular phone where it is what? Where it is you need to pay. So when they assign the licenses to the AT&Ts, to the Verizons, and so on and so forth, they need to pay money for it. Clear? We'll get to that shortly. Answer me the following. Each channel, each channel is 200 kilohertz. By the way, question, and maybe it's a premature question. How come each AM channel requires 10 kilohertz, whereas each FM channel requires what? 200 kilohertz. It's the same what? Information is audio. The audio information is the same. Yes or no? How? No response. Yes or no? How come this one is 200 kilohertz, this 10 kilohertz? We will see shortly that the FM is a what? It's a type of modulation that results in expansion of the what? Of the bandwidth. Do you follow me or not? It requires more what? More bandwidth because it will create multiple what? What is known as multiple sidebands. Whereas AM will create only a single what? A single set of sidebands, up sideband and lower sideband. Clear? Let's not worry into the detail. I want you just to get the idea here. How many channels are there? Still waiting. Channels. Question. Does that mean that there are only 100 channels in the US? FM channels in the US? So what does that mean? It means those channels are going to be what? Reused. That's the concept of what? Frequency reuse, which is a fundamental concept of RF communications, which is what? We can afford to reuse the frequencies as long as there is a what? A spatial separation between the transmitters. We cannot put two transmitters at the same place, transmitting at the same frequency, and don't expect any interference. There will be some interference. But if they are located far away from each other, the interference will be what? will be negligible or will not be existent. We'll talk about that later on. Clear? No response. Clear? Okay. How about the cellular? US cellular? Anybody? Well, this is the 800 megahertz band. This is, by the way, the G2G. 2G stands for what? Second generation. Anybody? D. Huh? What is D/L? U/L? Uplink from what? From mobile to what? From what? Base station to what? Mobile station. Anybody? Uplink? 824 to 849 megahertz. How much is the bandwidth? 825 megahertz. And the downlink is what? 869 to 894 megahertz. This one also is what? 25 megahertz. Question, how much is the bandwidth? How much is the bandwidth? Total bandwidth. Actually, the total bandwidth is 25 megahertz. Why? Because for each call, you are going to need how many channels? You are going to use 2 channels, one on the uplink and the other one is on the what? On the downlink. Did you understand what I just said or not? This is what we are going to be referred to it in just a second. What is known as what? FDD. What is FDD stands for? Anybody? Frequency division duplexing. I will explain this one to you in just a second. But let's not get bogged down with here. I want you to tell me, first of all, do you see the separation between the uplink and the downlink? How much? How much is the separation? 824. This one is what? 869. Which means there is a 45 megahertz separation between the what? Uplink and the what? Downlink. For what purpose? For the purpose that I was just telling you about. To what? To avoid interference from what? Any traffic going from the mobile. Are they transmitting at the same time? The uplink and the downlink. Are they transmitting at the same time? They are transmitting at the same time, but using different what? Different frequencies. Are you following me or not? As opposed to the other type, which I will show you shortly, which is called what? TDD. TDD stands for what? Time division duplexing, which means that you are going to be transmitting using what? Using a single frequency, but what? 2 different time slots. One time slot is for the uplink, the other time slot is for what? Downlink. They alternate. Clear? We'll talk about that shortly. But I want you to understand one thing here. Are all of these frequencies received by the antenna? They are all received by the antenna. Can we hear them? We cannot hear them. These are in the RF range. If we can hear them, what do we need a radio for? We just do it like this? Everything. We cannot hear them. Yes? We need, first of all, to select the band, not the channel, to select the band. Question. First of all, can you tell me what is each channel here? Anybody? 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 Nobody. The each channel is 30 kilohertz. This is a narrowband channel. This is not the 3G that uses what? CDMA. In CDMA, anybody knows what CDMA stands for? Code division multiplexes. We will see that it requires what? Wider channels here. We'll talk about CDMA in just a second. But what was the question? I forgot what the question was. Why can't we select the channel right away? Why can't we select the channel right away at the receiver side? We'll get to the transmitter in just a second. Why can't we select the channel rather than selecting the band? If we select the channel, remember, the channel bandwidth divided by F sub 0, F sub 0 is the what? Is the center. Okay, it's the other way around. I'm sorry. Raised to the power what? -1, which means what? F naught over what? Over the bandwidth is what is known as a what? Q factor of your what? Agree? Now, imagine if I'm going to select the channel right away. How much was the, give me an F0 in here, some channel. Let's say 8, just for sake of argument, 830 mega, divided by what? 30K, that results in what? In a huge Q factor, which means the design of the filter becomes what? Extremely complicated, bulky, and it will prevent what? The ability of integrating that filter within the what? Within our chip. Did you understand what I just said or not? So we take it what? We take it step by step. Do you follow me or not? At the beginning, we are going to do the what? The channel select. Now, before we get to the receiver, can we get back to the transmitter side? This is the transmitter. Yes? Okay. Where is it coming from? It is going to come from an information source. Information source generating what? Generating data. Most of the time, of course, the data is what? It's analog. It will be what? It will be digitized. Are you following me or not? It will be digitized. If it is already digital, like from a PC or something, then it is digital. Now, what do you see? This, we are going to be referring it to as what? As the IQ modulation. We don't know what that means yet. The I means what? The in phase, and the Q stands for what? The quadrature phase. So we divide our what? Excuse me. We divide our traffic or our bit stream in what? I want you to think about it this way. A bit stream is a stream of what? Zeros and ones. We take, for example, the odd, we are designated by what? The I channel. The even, we designate it as a what? As a Q channel. Clear? But it also could be what? Independent bit stream on the I channel and the what? Q channel. Did you understand what I just said or not? Yes or no? Does not have to be what? Alternating even and odd. It could be what? Independent. Okay. DAC. A DAC stands for what? Digital to analog converter. Why? Why do we need a DAC in here? Those signals, digital signals, has sharp edges. Sharp edges means what? They have, let's see if you remember from Fourier Transform. I doubt it, but let's see if you remember from Fourier Transform. If I have this, if you can tell me, I will be very happy. If you do have a single pulse here, okay, this is the T. This is F of T. Tell me, what is the Fourier Transform? It's a sync function. Do you agree or not? Do you still remember this or not? What do you notice about the sync function? The sync function is what goes on and on and on. Eventually, what will it hit? It will hit the adjacent channels, creating what is known as a what? Adjacent channel interference. ACI stands for what? Adjacent channel interference. As opposed to what type of interference? What is the other type? Anybody? It's CCI. CCI stands for what? What does that mean? Let's see, understand what this called. First of all, interference. Do you understand what do I mean by adjacent channel interference? Notice, by the way, we are not talking about what? Out-of-band channels. Out-of-band channels are easier, what? We can easily get rid of it through what? Filtering. Do you understand, or yes or no? I am talking about what? Channels within the same what? Within the same band, but they are adjacent to you. Clear? What does CCI stand for? Co-channel interference. When the channel is reused again. Did you understand what I just said or not? I will show it to you in a minute when we get to the cellular architecture. Are you following me so far or not? Okay, good. Now, this, so they need to smooth the edges of what? Of these pulses. These pulses, they need to what? Smooth the edges so that they restrict the what? The bandwidth occupancy. This signal here, we refer to it as what? BB. What does BB stands for? Do you see this BB? BB stands for what? Baseband. So BB. What do I mean by baseband? When somebody tells you this signal is a baseband signal, what does it mean? It means that its frequency, its Fourier transform, or its spectrum is centered around what? It's centered around the origin, low frequency components. Are you following or not? So for example, for voice, anybody? Bandwidth is roughly what? 4 kilohertz. Notice, by the way, what do I mean by the bandwidth? The bandwidth is the highest frequency. Remember, we are starting from 0, so the bandwidth is the what? Is the highest frequency component available. Always remember, by the way, the bandwidth is only measured for excuse me, positive frequencies. Are you following me or not? Although when you sketch the spectrum is a what? Two-sided. Did you get my point or not? The spectrum is two-sided, but when you measure the bandwidth, you measure it only on what? On the positive side. Clear? Okay. Notice, by the way, theoretically speaking, if you do have something like this, the bandwidth is equal to what? Infinity. Because this one will go on and on and on like I'm doing it right now. On and on and on. Are you following or not? So you need to take approximation. For example, you will take the what? The bandwidth of the first null. Null means what? The first time or the main lobe, if you want to think about it. Or you take the 90% what? Bandwidth, which means what? This is the bandwidth where 90% of the energy is what? Is concentrated or located. Clear? Okay, we'll talk about that later on. For video, for example, uncompressed or analog video, roughly 6 megahertz. High audio. Anybody? 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 Why did I say 22 kilohertz? This is the range of your what? Of your ear. So when you talk about audio, it means what? It has to be within your ear. Clear? Clear? Okay, good. Now let's get back to the diagram. Are you following me so far or not? So this is the I channel. This is the what? The Q channel. It goes through what? It goes through a low pass filter. Again, this is to smooth what? All the edges from the what? From the DAC. Are you following me or not? It's a low pass filter. This is a low pass filter. Now, what does it get into? It gets into what? Modulation. What is modulation? Modulation is the process of imposing. The process of, I will explain to you shortly in detail, imposing the information signal on top of what is referred to as a what? As a carrier signal. Where is the carrier signal coming from? It is coming from here. This is the VHF. What is VHF stands for? Very high frequency. We will look at the range in just a second. Very high frequency. LO stands for what? Local oscillator. It's a local oscillator. An oscillator is a device that generates how many frequency? One frequency. Are you following me on that? As opposed to a what? A synthesizer. A synthesizer is a device that will generate what? It's multiple frequencies, a band of frequencies. We'll get to that in just a second. This is the what? This is the frequency. Notice, by the way, this is not yet the carrier frequency. I will show you what the carrier frequency is in just a second. This is the what? The modulated, the output is what? The modulated carrier. It gets added together. Are you following me on that? It gets amplified in what is known as what? IFVGA. IFVGA stands for what? Intermediate frequency. What is the intermediate frequency? Intermediate frequency is this frequency. Yes or no? And VGA stands for what? Variable gain amplifier. Variable gain amplifier. You need to adjust the what? The gain of your modulated carrier appropriately. Clear? No response. Clear? What are we doing here? We are doing the up conversion. I don't want you to confuse the up conversions with what? Modulation. They could be the same. In other words, modulation could be also the what? Similar, I mean not similar, exactly is the what? Up conversion. But that's not necessarily the case. In here, the modulation is done in what? The modulation is done in here, whereas the up conversion is done in here. Where is the signal is coming from? It's coming from a UHF. UHF stands for what? Ultra high frequency, local oscillator. Are you following me on that? Now, we notice what is this? This one is being used both by transmitter and what? Receiver. That is the point, or that's the concept of reusing the hardware. You don't want to design what? Separate local oscillator for what? For the transmitter and what? For the receiver. You design a single block that will help both. We will see that this is actually a what? A synthesizer. Are you following me? A synthesizer, because you are going to what? Generate different frequencies depending on the desired channel. We'll get to the receiver in just a second. Are you following me so far on that? Okay. You go into a what? A driver, and then you go to a what? A filter type filter. Again, this one is to try to get rid of as much as possible from the out of band interference. Clear? Okay. Then what do you need to use? You need to use a power amplifier. A power amplifier is needed to adjust what? to adjust desired power. You have to remember that your RF signals is going to be propagating over what? Long distance. You need to have enough power to cover what? The range. Otherwise, you are not going to be able to reach what? It's not going to be able to reach the receiver. In the receivers or in systems that uses CDMA, CDMA stands for what? Code division multiple access. We will see shortly that in code division multiple access, mobile stations uses the same frequency, they transmit at the same time, but they use different what? Codes. In this case here, we are going to experience what is known as the near-far problem. Near-far problem means what? Means a receiver is going to receive a strong interfering signal from a transmitter happens to be nearby, rather than receiving a what? A weak signal, desired signal, from the desired transmitter, which happens to be what? Far away. We need to use a what? A power control mechanism to adjust what? The transmitter who is at a far away, transmit at a higher power. The transmitter who is what? Close by, it transmits at a what? Lower power to control the effect of the power. It goes all the way to the what? To the antenna. Notice, by the way, it will not what? It will not come in here if everything is perfect. Why? For the cellular system, there is already a separation of how much? I showed you that already a moment ago, a separation of 45 megahertz between them. That filter here needs to what? Needs to be able to separate the transmitter from the what? The receiver. If this one was a TDD system, time division duplexing system, then instead of this duplexer, we will use a what? An RF switch. An RF switch is what? When you are transmitting during your time slot, the switch will be on this side. When you are receiving, the switch will be on what? On that side. Because in a TDD system, you are going to use the same frequency. Clear? We'll get to that shortly. Let's continue. Again, all of this, we will study them in detail. They're just an overview. Clear? Oh, it comes. The receive signal. Is the receive signal, by the way, what did I select? I selected the band. I did not select the channel yet. I selected only the what? The band. Is the receive signal weak? Okay, let's see if you get the idea about how weak it is. Let's see if you can help me here so that you understand. Assume receive signal power is minus 100 dBm. Do I need to explain to you the dBm stuff, or you know it? What is this dBm? I'm not sure if you know it or not. Do you or not? Is this power, or is this gain, or in other words, what is the difference between dBm and dB? dB is a gain or attenuation, whereas dBm is what? It's power. I'll explain this one to you next time. Let's not worry about it. All what I'm trying to tell you is that this one is equal to what? 10 to the minus 10 milliwatt. MW stands for what? Milliwatt. Okay, which means what? 10 to the minus 13 watts. Clear? Okay, what is the peak value of peak value voltage of received signal at antenna of 50 ohm impedance? This is, by the way, later on we will designate it by what? Z0. Clear? Anybody know Z0? That's what we are going to be referring to it as the characteristic impedance. Don't worry about it. Don't worry about it. I'm still waiting. What is the peak volt? This is the average power. This is the average power. Well, how do I get the voltage? So what? 10 to the minus 3 equal to, I'm sorry, not minus 3. 10 to the minus 13. I'm sorry. 10 to the minus 13. I'm still waiting. B square. 2. Did you understand where the 2 came from? Where? This is sinusoid. So when you calculate the average, there will be what? There will be a 2. Don't worry about this. The point right now, I will show it to you later. The point right now is that I want to show you how small the voltage is. From here, you will get what? You will get V is roughly 3 microvolt. High or low? This is low. You would think, you would say what? You think, what is this 3 microvolt? What am I going to do with it? What does that tell you? It tells you that the receiver needs to provide what? Amplifications along the way. Are you following me on that? Now, the question is what? Should I put all the amplification in one amplifier? In other words, I design an amplifier with all the amplification. The answer to that is what? Is definitely no. You are going to spread the amplification around what? Around the chain of blocks at the receiver side. You have to always remember one thing. What does LNA stands for? Low noise amplifier. What does that mean? The low noise amplifier is a device or an amplifier that will introduce minimum noise, internal noise. We are not talking about what? External noise. Is there external noise here? How come the filter did not get rid of it? Wasn't there a filter here? How come it did not get rid of the filter noise? Noise, if you remember white noise, what does the spectrum look like? Constant across what? All frequency components. So no matter how what? No matter how selective your filter is, there will be what? There will be noise getting in. I don't want to add to that noise more noise internally generating from what? Generating from the low noise amplifier. Did you get this or not? Yes or no? Now, imagine if there is a transmitter. What was the power here? How come the power was very low? Minus 100 dBm. How come it was very low? It was very low because the transmitter, the desired transmitter, happened to be what? Very far away from what? The desired receiver. Imagine if there is a close-by transmitter, not the desired transmitter, but a close-by transmitter at a power of, let's say, 10 to the minus 4. I said 10 to the minus 4. Minus 40 dBm. Minus 40 dBm, if you plug it in here, the power will become what? 10 to the minus what? 4. And when you plug it in here, you will get roughly, instead of 3 microvolt, you will get what? 3 millivolt. Which means what? Which means the interferer is what? Is 100? No, 1,000 times. 1,000 times as the desired signal. Agree? If you put all the amplification in one unit, what does that result in? It results is that you are going to amplify the what? You are going to amplify the interfering signal in such a way that it will block. We will see what the meaning of the word block later on. It will block the entire receiver. Did you get this or not? Which means what? What do I need to do to, first of all, to the interferer? I need to what? I need to filter as much as possible from the interfering signal before I what? I achieve all the amplifications of the desired signal. Did you get my point or not? Yes or no? Details are yet to come. It's just an simple. Okay, you see a filter here. What is this? By the way, what is BF? BFF stands for? This is not the best friend forever or something. BF stands for what? I cannot believe I said that. You know, I'm old, so sometimes I act as a senile person. So don't take me seriously. PBF stands for what? Band pass filter. Why? What is this one is doing? This one is what's known as what? Image reject filter. We don't know what image reject filter here, but I need you to understand one thing here, is that if a carrier signal is what? You see, remember what I told you. This is what is referred to as a what? A super heterodyne receiver, which means that we are going to what? Down convert, first of all, to the IF, and then what? To the baseband. Are you following or not? When you convert to the IF, you are going to mix. What is this, by the way? This is a down converter, which is referred to as a what? As a mixer. What are you mixing? You are mixing the carrier signal with a what? A locally generated carrier, such that, always remember, by the way, when you mix two, question. What is cosine? Omega 1t, cosine, omega 2t. What is this equal to? Anybody? Trigonometric, this equal to what? 1/2. Yes or no? Which one do I want to retain at the receiver side? At the receiver side, I want to retain this and I want to filter this. Did you get this or not? On the transmitter side, which one do I want to retain? I want to retain this one and I want to what? Filter this one. It's the other way around. Clear? Now, when you mix two signals or two carrier signals, there is what is known as the image. So if this is what? If this is omega naught, which is the what? This is the local oscillator. Yes? If this is the desired carrier, yes or no? Where is the IF? The IF will be from where to where? The difference. Yes or no? But if there is another what? Another carrier here, which is what? The same separation as the what? Local oscillator, but on what? On the upper side. What will be the difference between this one and this one? The same also as IF. Yes or no? This is called the image of this. Did you get this or not? In a direct conversion receiver, in a homodyne receiver, we are not going to have that problem. Why? Because in a homodyne receiver or a direct conversion receiver, the local carrier is equal to the what? It's equal to the what? To the received frequency. You lost me here. To the carrier frequency. Did you lose me? Hey, you lost me. Did you lose me? Hey, you lost me. Concentrate. Can you concentrate? Down conversion is converting the what? The RF signal directly to who? To the baseband, which means centered around what? 0. Which means the local carrier generated locally at the receiver needs to be equal to what? To the carrier frequency, received carrier frequency. So there is no what? There is no image. By the way, one of the beauties that we will discuss when we look at the different architectures of the transmitter, one of the beauties of the direct conversion is that it does not need a what? An image reject filter. Did you get this or not? There is no image. It's the same thing. Clear? Okay, let's not worry about it. What is this one is doing? This one. This one is the image reject filter. You follow me or not? Notice, by the way, if the image happens to be what? Out of band, then I don't have a problem. Did you understand that or not? Why? Why I don't have a problem? Because it had been already what? Filtered out by the band select filter. Did you get this or not? But if the image is within the band, I need to get rid of it. That's this one. So this one is the what? What is IR stands for? Image reject. Again, don't worry about it. Just get the buzzwords right now. All of them, we'll study them in detail. What is this one is doing? This one is down conversion. The mixing. Is this frequency? Look at my finger. Is this frequency fixed or variable? This one is fixed. As I said fixed, I'm sorry. This one is what? Variable. The difference between them, between the carrier frequency and what? The locally generated carrier is what? Is fixed. That's the IF. Anybody knows what the IF frequency for AM? AM, the one that we talked about here. Where is it? AM, IF. $455 kilohertz. By the way, an important parameter in the design is that how do we choose the IF? How do we choose this IF frequency? Why did they choose 455 kilohertz? That we will study as we move along. FM, anybody? Anybody? 10.7 megahertz. By the way, I'm not asking you to memorize these numbers. I just want you to get a feeling of them. Do you follow me? I'm not going to ask you questions like this, but I want you just to get a feeling about these numbers. Clear? Okay. Now, the IF is fixed. Is the carrier frequency fixed or is it variable? Variable depends on which channel you are interested in. Yes or no? Okay, so this one is going to be what? Variable, which means what? This is, even though it says UHF local oscillator, but in reality it's a what? It's a synthesizer, generating what? It's on, in other words, think about it as this way. It's a variable what? It's a variable oscillator. Are you following me or not? Yes? We will refer to this later on. We will refer to it as VCO. VCO stands for what? Anybody? Voltage controlled oscillator. It's an oscillator whose frequency is going to be controlled by a what? By an input voltage, using what is known as a what? As a phase lock loop. We'll talk about that later. Clear so far? What are we going to get here? What are we going? We are going to get an IF signal. We amplify the IF signal. This is the IF amplifier. Are you following or not? And try to what? To filter as much as possible the what? The remaining band, because you have to remember any nonlinearity in a device will result in what? Will result in what? Harmonics will result in what? Regrowth of the spectrum that you what? That you filtered out. Look at the dilemma. We are trying to what? See this one here? We are trying to filter out any what? Any excursions of the spectrum outside the desired band, outside the desired channel, only to be what? Recreated if your power amplifier was what? Nonlinear. Did you understand that or not? Cannot hear you. Now, for constant envelope modulation schemes, anybody knows what constant envelope means? Constant envelope means what? Means the amplitude is what? The envelope is not changing. Can you give me an example of a constant envelope? Or in the digital scheme is MSK, for example. MSK stands for what? The minimum shift key. Clear? Or GMSK, and so on and so forth. Nonlinear power amplifier is preferred. Are you following or not? But for those modulation techniques that has a what? That has a variable what? Envelope. We need to be careful with the what? With the power amplifier. We need to use what? A linear power amplifier. Otherwise, all of these regrowth, otherwise all of these side lobes will what? Regrow. In other words, we filter them out from one side and they what? They grow from the other side. Do you follow me or not? Now, don't tell me, let's filter them out again. Once you filter it out again, you are going to introduce what? In attenuation. Every filter you introduce it's an insertion loss. Did you get my point or not? Okay. So keep that in mind. So in here, you are going to filter out any of these, amplify it with a certain amplification. What is IFVGA? IFVGA is what is the IF, variable gain amplifier. Again, yes? What are we doing here? What are we doing here? We are demodulating. You notice I call this one a what? A down conversion, whereas I call this one a what? A demodulator. This is the VHF local oscillator. Are you following me or not? Separated again. Do you see the 0 and the 90? What does that mean? Here is generating what? A cosine, for example. This one is generating a what? A sine. This is the IQ, demodulation. Clear? So we demodulate. We use a what? A low-pass filter. Why? Can you tell me why are we using a low-pass filter? Is this mixing? That's mixing. Always remember, when you mix things, you are generating the what? The sum and the what? Difference. I need to get rid of the what? The sum. So I use a what? A low-pass filter to get it up. Clear? Amplifier, these are the I channels or the Q channels. These are what? These are the baseband amplifiers, or what is known as what? The audio amplifiers. Clear? The audio amplifiers. And then I change it into what? Into ADC. ADC stands for what? Analog to digital conversion, analog to digital conversion, and then what? To the baseband processor here. Now, what is this baseband processor here? You could have used what? Error correcting mechanisms. You could have used encryption. You could have used multiplexing. All types of processing that will be done in the what? In the baseband, rather than in the what? In the RF. Now, could we have used the ADC or in the ADC, the analog to digital conversion? Could we have used it all the way here? Are you following me or not? That's the concept of what is known as what? Software-defined radio. Everything is what? Trying to what? To perform most of the functionalities in what domain? In the digital domain, rather than in the what? In the analog domain. But the problem that we need to face is what? Is that you have to remember that when we talk about analog to digital conversion, how many processes are involved? 3 processes. The sampling, the quantization, and the what? Encoding. Yes or no? Okay, sampling, we already know from Nyquist, telling me what? Telling me that if you want to recover the analog signals from its samples, you need to sample at least twice the highest frequency component in the signal being sampled. Clear? And if I'm going to sample at the RF, what does that mean? It means I need to use a huge what? A huge what? A huge number of what? A huge number of samples. And we will look at all of these issues shortly. Clear? Did you get the idea or not? We are going to be looking at each one of these blocks, and we look at them in detail, not just what? Words. In other words, this power amplifier, I'm not going to tell you this block uses what? Uses or amplifies the power. We need to understand how does it do that, the circuit design, and so on and so. Notice, by the way, what is here missing in this diagram is that we need what? At the output of the power amplifier, we need a matching circuit. Most important in RF design, you need to make sure that the output of the power amplifier is matched to the what? To the input impedance of your antenna. Are you following or not? Otherwise, there will be a lot of what? There will be a lot of power that is what? Reflected back, which means what? Not transmitted, wasted. Clear? So we are going to be looking in detail into the impedance matching issues and so on and so forth. Clear so far? Yes or no? In details. This is just a what? Think about it as what? Coming attraction. You go to a movie, there's a coming attraction. Then we will what? We will study them in rather some detail. Now, let's get back to the notes. I want to show you. I found it finally. I want to show you why, before I get back to the start of the notes, I want to show you why is the RF. Can you zoom back? No. That's okay. I have what? I just started. I have only 5 minutes left. Oh. Okay. Now, it doesn't matter. We'll continue next time. I want you to concentrate here. Do you see why it is so complicated, RF? Look at all the fields that communications theory, which means what? You need to know a little bit about modulation. You follow me or not? You need to know about filtering, signal analysis, and so on and so forth. Random signals, that's a probability class. Why? You are dealing with noise. So you need to understand what random signals. Transceiver architectures, I already showed you what? The super heterodyne. We will look at what? Different architecture. For example, the direct conversion architecture. We will look at what? The low IF. Are you following me or not? We will look at the what? SDR, which is this, the software-defined radio. Briefly, I will give you a tutorial on cognitive radios and so on and so forth. Clear? So different types of architecture. IC design, designing all of these. By the way, if you notice in here, what are these blocks mean? What are these blocks mean? These are chips. So this is a chip, this is a chip. This one is what? It's out of chip. Out of chip means what? It's you need to take a wire from here, taking it what? To the outside and then back to the chip. Do you understand? And once you have all of these wires, it means what? You are going to go through what? You go through a lot of parasitic capacitance and so on and so forth. You need to make sure that those wires are what? Short wires. Did you get my point or not? So IC design here, CAD tools to simulate, as I will show you shortly. Microwave engineering, you need to know about what? You need to know about the propagation and so on and so forth. Wireless standards, all of these wireless standards. I want you to take a look, just briefly. I want you to look at this. This is what is known as a what? As a multi-mode. I want you to understand the terminology. When the question tells you multi-band, multi-band transceiver, what does it mean, multi-band? It means within the same standard, it operates in multiple bands. For example, GSM, what does GSM stand for? The Global System for Mobile Communications, operate in the what? In the 900 megahertz band. It operates in 1800 megahertz band. It operates in 1900 megahertz. 1900 means what? 1.9 gigahertz. Yes? If you are designing the receiver, a GSM receiver that operates in all of these bands, we call it a what? A multi-band receiver. But when you talk about a multi-standard means what? For example, look at this. The Bluetooth, the cellular, the application processor, the WiMAX, the wireless LAN, the direct video broadcaster, the GPS, the FM, XM, and so on and so forth. This, we call it a what? A multi-standard. If you deal with multi-standard and multi-band, you are going to get what is known as a what? A multi-mode receiver. So in a multi-mode, when you talk about a multi-mode, it's combination. So wireless standards, multiple access. Why multiple access? We have a shared media. A shared media means what? Means that we are going to be what? Requiring sharing of the media. I will show you that next time. But I want to show you one thing quickly. Sharing the band, sharing the channel. You can either share it in a frequency. We call it what? FDMA. FDMA stands for what? Sir, hey, the class is not over yet. This is not Starbucks here. FDMA stands for what? Frequency division, multiple access, where we are going to divide the band into multiple channels, frequency channels, and assign it to each user. we have what is known as what? TDMA. TDMA stands for what? Time division multiple access, where we are going to use the same frequency, but we will divide its usage into what? Into time slot. I'll show you this next time. CDMA stands for what? Code division multiple access, where we are going to be transmitting at the same time using the same frequency, but using different what? Different codes. Clear? These are medium access control procedures. Now, the last one, which is the what? Which is the space. I don't know what it is. I'm so disordered here. What is this? This is the cellular architecture. Look at it. This one here is this, the frequencies in here is going to be the same as the frequencies used in here. This is called what? Space division, multiple access. Space division means what? They are spatially separated. Clear? Spatially separated, that they can reuse the frequencies in here. Clear? All of these are for what reason? The reason being what? The channel is a what? It's a shared channel. The resource is a shared resource. You need to be able to what? Separate them. Signal propagation. This is, by the way, EE535. So if you are taking EE535, the emphasis of EE535 is this one, which deals with what? Which deals with modeling of the channel to introduce all types of what? Anomalies such as what? Such as slow fading, fast fading, multipass, all types of what? Reflection, diffraction, scattering, and so on and so forth, or modeling of the channel, and so on and so forth. By the way, I strongly recommend that you take 530. How many of you have taken 535? Okay, good. I like that. How many is taking 535? Okay. The rest of you, think a little bit about it, because those two courses complement each other. But 535, again, is purely what? Theoretical. It's not going to get into circuit design and stuff like that. Clear? Now, you can see from this diagram, there are a lot of what? A lot of things to cover. Are you following or not? A lot of this to cover. Now, keep in mind, our interest will be on the transceiver architecture stuff. Clear? Clear? Okay. Okay, let's continue. Do we still have time? I was dreading this one when I go. Okay, we'll continue next time.
The time is 11 o'clock.